Yeah, so I'd like to welcome everyone who's joining us this morning. Welcome to MIPI DevCon 2021. I am Justin, the MIPI DevCon chair, and thank you all for attending this year's virtual event. As I mentioned earlier, we had a great opening session earlier this morning for me, last night for you in Asia, and we're excited to bring you this special content in your local time and your local language. So a little bit of housekeeping before we start. At the start of each session, please visit the chat. You'll see the chat on the right on the purple ribbon. You will find a link to the transcript of each presentation, which has been made available. The translations are available in simplified Chinese, traditional Chinese, Korean, and Japanese. There will be a live Q&A to follow each session. And all presentations will be available after the event at mipi.org. So if you missed a session or you want to share with a friend, feel free to do so after the event. Also, please make sure to visit our demo booths. We have a lot of great demos from our demo sponsors, and we'll have more information about our member demos there. And on that note, I would like to give a big thank you to all of our speakers, all of our demo participants and sponsors. And I'd like to introduce today's sponsor for the special Asia track tonight, Introspect Technology, who will share a short message.
Welcome everyone to the Asia track session on MIPI I3C signal integrity challenges on DDR5 server-based platform solutions. The speakers are Azuena, Juan, and Nestor from Intel Corporation. Azuena is a signal integrity engineer working on Xeon-based server solutions. Juan is a platform architect at Intel, and Nestor is an analog engineer with 10 plus years of experience in signal integrity. Ashwina, Juan, and Nestor, over to you for the presentation.
Hello, my name is Juan Orozco. My co-workers, Azucena Lupercio, Nestor Hernandez, and myself from Intel Corporation will present the I3C signal integrity challenges on a DDR5-based server platform solution. The agenda for this presentation is to go over an introduction, an overview of the DDR5 SPD server connectivity and bus characteristics, to review the I2C and the MIPI I3C retrocompatibility challenges, to review the I3C controller and target device buffer on-resistant design implications, a deep dive on the critical time margin calculation and how the different AC/DC parameters impact the operating frequency of an implementation. We will show you the non-monotonic signal behavior that we observe in this application and why a slope reversal capability in the device targets were required in order to improve the timing margins and as well the logical proper functionality of the device. At the end, we will summarize all these details. So let's get started. The MIPI I3C improved inter-integrated circuit interface is first introduced in a server application for the DDR5 dual inline memory module serial presence detect, or the SPD DIMM function. Its implementation in a server by far exceeded the boost capacitance comprehended in the MIPI I3C basic specification for both the low and the high boost capacitance, as this specification was defined with mobile IoT, small handheld devices applications. This presentation covered the interoperability challenges that we have in a DDR5 server application because of the dynamic push-pull and open-drain nature of the operating modes in an I3C basic solution. We will cover an in-depth analysis of the implications of very long PCB traces in a motherboard, having memory module routing branches with several loads, and how all these characteristics impacted the electrical and timing parameters. The I3C communication bus specification was released by MIPI Alliance in 2016 as an improved communication protocol compared to its predecessor I2C. But the implementation of I3C in a data center or a server application was materialized only until 2020 when we have the first DDR5 samples. The main enhancements in I3C adopted by the DDR SPD functions are, of course, the higher bitrate. We can reach theoretically up to 12.5 megahertz compared to 100 kilohertz up to 1 megahertz of an I2C SPD function in prior DDR generations. Depending on the practical implementation, we can get any range between 12.5 to 125 times higher bitrate. The better I/O electrical interface, having a push-pull driver versus an open drain only buffer, it is much better for this type of implementations. The support for in-band interrupts or IBIs, which currently is not used by the DDR5 SPD right now, but we are looking to support this in the future and as well for other server use cases. The use for CCCs direct or broadcast, which provides as well benefits from communication from target devices and controller devices. And of course, the reduced interface power, which is now 1 volt I/O. The DDR5 SPD interface transitioned from I2C to MIPI I3C based on the following requirements for the next generation DDR DIMM technology. Number one, the lower I/O operating voltage. We can get as low as 1 volt, which is in line to the advanced silicon process node. In prior generation, the DDR4 SPD was used as 2.5 volts I/O, which is now not compatible with these advanced silicon processes. And even when looking into 2 or 4 years from now, then 1 volt I/O is what is required. The higher interface bitrate. In DDR4, we used to DIMM compared to 5 devices in a DDR5 application. In order to manage the increased number of devices, we need a higher bitrate. If you consider that we can have up to 8 DIMMs per SPD segment, this would represent a total of 16 devices in a DDR4 application versus 40 devices to be managed in a DDR5 application. So it's more than double. The actual implementations we are seeing is I2C can reach up to 400 kilohertz, limited by 2 factors, which is the open drain nature of the signal. We have problems with rise time and high boost capacitance in order to reach higher than 400 kilohertz. And the second problem is the standard I2C devices, such as I2C muxes, are limited to 400 kilohertz. In I3C, we are reaching anything between 8 to 12.5 megahertz in real application, depending on the number of DIMMs we have in the interface. The higher bitrate as well is required in order to reduce the boot time of the computer. It will diminish the amount of time the memory reference code has to spend in the overall DIMM discovery process. Let's review this connectivity of the DDR5 SPD in a server motherboard. If we look at DDR4, as I mentioned, per DIMM. One is the SPD memory and temperature sensor, and the other is the registering clock driver circuit. These two devices are interconnected to the platform I2C interface via this 2.5 I/O voltage to the target controller device in the platform, which could be the host CPU or the board manager controller. These devices operate in 1 volt or 3.3 volt, depending on the device. So there is a need of a level shifter in between. If we move to the DDR5 SPD, now you can see the platform controller, which is the CPU or the BMC, can be connected directly to the DIMM interface via the 1 volt I3C IOs. In the DIMM, we have 5 devices. One of them is the SPD I3C hub, which provides an electrical isolation between the host side interface and the local side interface on the DIMM. This isolation basically allows this controller on the platform to see the electrical load of only one device instead of the electrical load of 5 devices at the same time. So that helps in overall reducing the capacitance of the bus. The drawback from this approach is that SPD hub will introduce a time delay of 6 nanoseconds per direction or 12 nanoseconds round trip between the controller and target devices. At the end, there is a trade-off between the boost capacitance the phone controller would have to drive versus this 12 nanoseconds delay to be considered in the timing analysis. Now I will let Nestor to take it from here.
Yeah, well, thank you for the introduction, Juan. Then let's dive into the SPD boost characteristics. Now, the main issue, as you might notice from the diagram, is that the where we place the components, it's a real challenge. Why? Because the CPU and DIMMs being closer, but the BMC is up the north, right? So if you see this, the sheer size of the board is 16 by 19, which gives us a really big routing line that easily exceeds the 50 inches. So being the SPD a low priority, this is routed after the PCIe, the DR, or the highest speed signal. So that's the first challenge we had to overcome. The next challenge is how the actual connectivity is there, right? Because we have lots of branches, but you can see we have 8 DIMMs which have to be branched, and we have really long routes. So if we add up everything, like all the loads that we have per each DIMM, all the routings, then we have around 200 paths of capacitance that the driver has to manage all the time, right? So this will leave us with the next question: how is going to be the retrocompatibility for this kind of big size bus capacitance, right? Now, the first challenge is because I2C has to be compatible with I2C. We have to take a deep dive into what is I2C requirement. I2C requires have an open drain buffer class and requires a strong pull-up. Being an open drain requires a strong pull-up to get to the higher low, to the low high. Now, the problem with the I2C is this requires a push-pull buffer. That means we require a weak pull-up, so we can actually move the logic levels. So the MIPI I3C basic spec requires a dynamic pull-up to control to switch between the strong pull-up that requires the open drain and the weak pull-up that we require for the push-pull in the new I3C mode. So using 3 figures of merit for this, these 3 figures are the rise time, which is the next is the fall time and the BOL, right? So you can see on the right side that the open drain has the lower value for the resistors, and then the push-pull on the left side, we require higher values of the resistor, right? So if we do the parallel equivalent for these 2 requirements, we arrive to a sweet spot. This sweet spot is around 333 ohms, which will give us a rise time of around 75 nanoseconds. And with this pull-up, we also have a safe and healthy BOL value that is required to meet the highest operating frequency. Now, the add-on. The driver that has to drive, you remember, is a 200 PAF bus, has to be a strong driver. We require a 40 ohm strong driver, which will give us this kind of characteristics on the over trace length. So you see when we reach the 50 inches and so on, we can see how the ROM still managed to drive that capacitance, right? But we have some issues. The first issue is that the ROM will reduce the BOL. With the longest trace, we will have around 146 millivolts. And if we have a BIL threshold of 300, we'll have around a margin of 150 millivolts, right? Now, the problem here is you have to notice that current that is being used is 3.60 milliamperes, which is kind of not noticeable for power consumption, right? So we can limit the ROM into a max range of 4 ohms, which will ensure a healthy VOL and a max current of no bigger than 3 milliamperes. That will be the main features for this buffer on the I3C design. Next, we can jump to the actual connectivity and calculations.
Thank you, Nestor. Now let's talk about some critical time margin calculation. In order to identify which will be the correct operating frequency for high boost capacitance systems, we will need to check the setup time margin when target device is driving to the primary device. That can be done by the following equations. By knowing that the transaction is made on the low part of the signal period, then we will need to subtract all the propagation delay parameters that are present on the full path, such as the clock flight time propagation delay from the primary device to the hub device, the clock propagation delay of the hub, the clock propagation delay from the hub to the target, the data TCO of the target, the data flight time from target to hub, the data propagation delay of the hub, the data flight time from hub to primary, and then the setup time of the primary device. By having in mind these equations, we can now identify which are the most critical parameters to check when we are identifying the operating frequency, such as flight time, that is trace length dependent, the inner propagation delay of each device, and the TLO. On upper figure, we can see by increasing the trace length, the flight time will also increase. That means the flight time can be very high at high trace lengths. Then, the highest the propagation delay will be bigger the time margin reduction. However, increasing the TLO can provide an extra time margin. On below figure, we have 3 operating frequencies, 12.5 MHz, 10 MHz, and 8 MHz. The red one is the 12.5 MHz. As you can see, even when we have very short trace lengths, the time margin is very short. That means there is not enough time to complete the signal transaction. Then, for 10 MHz, we have a wider range of solution space of about 35 inches. And finally, for 8 MHz, there is a wide enough solution space for high capacitance pulses that we can go higher than 40 inches. Then, knowing that TLO is one of the most critical parameters, then we can have into the game 3 new parameters, such as duty cycle, clock digital high period, and clock high period. So, increasing the duty cycle, the TLO will be reduced. That reduces also the time margin. When reducing duty cycle, the T high and TD high are affected. That means small duty cycle can produce a not passing on the T high and TD spec. That is, the T high minimum is 24 nanoseconds and TD high minimum is 32 nanoseconds. So, a correct selection of duty cycle can provide an extra time margin to complete the setup transaction. This will guarantee a higher operating frequency. The non-monotonic signal behavior. A non-monotonic signal can be mitigated by a determination effect. That means when we have not terminated circuits, the signal bounce back and forth between the driver and the receiver. And as the signal have non-monotonicities present in there. Then the transmitter terminated circuit reduce the drive strength, increase the propagation delay, and limits buffer capabilities. This one also have non-monotonicities present. The transmitter-terminated circuit reduce the bouncing effect, but the time propagation delay is very high. In here, the blue line, there is no monotonicities present. The slope reversal capability and timing improvement. With a non-deterministic loading on an unterminated bus, there can be reflections on the bus causing the slope reversal on the receiver signal. If we sampling on the first threshold, it is possible to filter the non-monotonicities or Smith trigger inputs. By comparing the non-terminated buses versus the receiver terminated, the flight time improvement is about 2.3 nanoseconds. Then comparing non-terminated circuits versus transmitter terminated, the flight time improvement is higher, about 3.9 nanoseconds. The slope reversal capability provides an additional time margin that improves the operating frequency and prevents false logic states. The summary. I3C applications in server systems such as DDR5 SPD are dealing with high bus capacitance than the maximum allowed limit assumptions in the I3C MIPI spec, that is mostly for 12.5 MHz capable buses. Higher bus capacitance application can be mitigated by using buffer drive strength, strong open drain class for pull-up, and hub insulation circuits. A dynamic pull-up operation allows to drive the interoperability challenge between the open drain and push-pull operating modes by enabling higher operating frequencies on both modes and limiting critical parameters to meet latest specification. A strong buffer tend to increase signal energy reflections, especially in complex topologies, resulting with a slope reversal condition at device inputs. The Smith trigger capable inputs are required in order to mitigate the slope reversal condition when dealing with high bus capacitance and strong buffers. Thank you very much. We all appreciate your attention, and now we can go ahead to the question and answer session.
To start with, can you explain what kind of load capacitance did you use or consider on the board side for this problem statement?
It was like around 200 buffs.
Around 200 buffs. Okay.
Yeah.
And what kind of trace length is the solution working out?
I think it was around. And do you remember the exact number of the trace length?
It's about 24 inches.
Yeah, 24 inches on the motherboard, and each of the DIMMs, they have a branch, right, of roughly 2 inches or so, right? So the 150 picofarads is inclusive of all DIMM branches and motherboard routing.
Okay. All right. Audience, please post your questions online so that I can pick it up. I don't see any questions so far. And what kind of frequency to capacitance ratio will this proposed solution work?
For this one, on one of the slides is show we can reach at about 10 to 8 megahertz, depending on how long do you go on platform and the combination with the number of loads. And also in the case of the DIMMs, including the segment of trace length that it is also include. So for long trace lengths, the recommendation is to not go up to 10 megahertz.
Okay. Audience, please post your questions if there are more. I have one more question for you folks. The main focus is the slope reversal effect here caused by high bus capacitance, right? Is there a way to avoid the slope reversal?
there is no way to avoid the reflections because on long trace lengths, this is a common effect that we can see. However, we can use devices that have the capability to handle this kind of non-monotonicities, such as in this case, the hub have this slope reversal capability. And also, one other thing that we can do is to tuning or use the correct R-on or buffer strength of the driver, and that will also reduce the non-monotonicities. In addition, a series termination resistor on the receiver point that also mitigates the non-monotonicities. However, that will depend of the system that we have
Okay.
and the requirements that it have.
And just to add on that is, once you try to mitigate all these slope reversal, the slope reversal is for the reflections on this high complex branch topology, right? And all these mitigations that Azucena mentioned will have as well an implication how fast you can run this interface, right? Because by reducing the drive strength, then it means the buffer will be less capable to drive high boost capacitance. By adding termination resistors at the receivers, as well will slow down, right, the rise and fall times. So at the end, yes, there are ways to mitigate slope reversal for these complex multi-point topologies, but then you will have to pay the price for slowing down your interface.
Thank you. I don't see any more questions from the or any questions from the audience, so I'll stop with one last question then. Do you have any thoughts and recommendations for the I3C spec to actually take your solution from beyond 10 megahertz that you are saying for your topologies?
That's a very good thought, a very good question. For example, from the JEDEC point of view, right? That JEDEC adopted I3C basic, they are indeed adding this slope reversal capability requirements on the DDR5 SPD hub. And it would be good, right, from an I3C work group point of view, having or adding this type of input characteristics, right? I mean, Smith trigger or the slope reversal characteristics, so that we can make it easy or mitigate this type of problems, especially in some of these complex server form factors where the systems are just huge, right? And in the future, we are looking to use I3C for other applications that I3C may be running through cables, multiple PCBs. So that is going to be very challenging from a signal integrity point of view.
All right. Thank you, Azuena, Juan, and Nestor. Very good presentation and insightful. Thanks all audience for joining the session of the MIPI DevCon.